So I'm going to be talking about some work that I've done recently with my advisor, Tom Mitchell, and with Diru Dua, a master's student at CMU. And the work that I'm going to be talking about focuses on knowledge bases. These are large collections of facts. I'm sure most of you have worked with knowledge bases in the past. They're facts about people, places, and things in the world and relationships between them. There's been a lot of investment in resources trying to construct these large knowledge bases, either through crowdsourcing with Freebase or automatically with the Null project and other things. And why do people care? Well, one thing you can do with them, if you're Apple, you could take this knowledge base and build a speech interface on top of it so that you can take what someone says, convert it into a query over this structured knowledge base, run the query, get back some structured information, and present it to the user. And this is really helpful. Similarly, if you're Google, you can take a query that someone types into a search bar, convert it to some structured representation that you can query over your knowledge base, and return something that's a lot more interesting as search results. So Google here knows that Quentin Tarantino is a person who directs movies, and so it can convert this string into some interesting query and get back the list of movies that Quentin Tarantino has directed, and some structured information about the person himself. And these are all well and good. They're really useful applications. But somehow, to me, it's somewhat unsatisfying, because really what we're doing is treating these knowledge bases just as databases, things that we can look up facts in. This is really good. But somehow I think the real promise of these large collections of knowledge bases is to use them to get computers to read better. And that's not really what this is. Another way to think of this is how can we use these knowledge bases to do better natural language processing instead of just looking up information from this text, from the knowledge base. And a lot of people are working on this problem. You here at AI2 are working on this problem. I haven't solved it. You haven't solved it. But here's some ideas that I think can get us closer to actually using knowledge bases in machine learning models. And the things I'm going to talk about today involve looking at the knowledge base as a graph, and then extracting characteristics of that graph to use as features in machine learning models. That's the key point of what I'm going to talk about today. And so first I'm going to introduce a method that is one of the only prior methods that I'm aware of that can use a knowledge base more directly in a machine learning model. And I'm going to talk about some deficiencies there and introduce a new technique that I call subgraph feature extraction, and then show some applications of this in a few different problem settings. So this first technique is called the path ranking algorithm. This was introduced by Ni Lao at CMU a few years ago. And it's an algorithm for doing link prediction in a graph. That is, if you have some graph with labeled edge types, what this will do is, and you assume that this graph has some edges that are missing, say it's an incomplete knowledge base, this algorithm will let you learn models that will predict new instances of each edge type in the graph. And Ni, when he introduced this, thought about it as an algorithm for link prediction. I'm going to describe it just a little bit differently as a method for generating a feature matrix over node pairs in a graph. I'm going to do that because I think this method is a little bit more widely applicable than Ni ever used it. So that's how I'm going to describe the method. So here's an example graph. It has facts like the Maple Leafs are a team that plays in the league NHL. And what we want to do here is find edges that are missing. Like, say, GM should have an economic sector edge for the automobile sector because it's an automobile company. How are we going to do this? Well, the way the approach the path ranking algorithm takes is similar to a logical kind of inference. So one common technique is horn clause inference. So you find a set of rules of the form, if x1 competes with x2, and x2 participates in the economic sector x3, then you can conclude with some probability that x1 also participates in the economic sector x3. You notice this is a particular kind of horn clause. It corresponds exactly to a chain in this graph. Indeed, there's an instance of that chain here. GM competes with Toyota. Toyota participates in the economic sector, automobile. And so from this graph and this rule, we can conclude with some probability that GM also participates in the automobile sector.
Wouldn't you have a really large company, like, say, Microsoft, that works in the operating system?
Indeed, I was just about to say that this rule isn't perfect because companies can participate in many economic sectors, and the sectors that they participate in may not overlap. And so this rule could lead you astray, potentially. In this instance, it'd be correct. But what you would really like is to find a lot of these rules and be able to combine their evidence in some principled way. That's what the path ranking algorithm does. It takes a two-step approach that first it does a search over the graph given some training data to find these rules. And then the second step is it uses the rules that it finds as features and computes a feature matrix over node pairs that it can use, then uses logistic regression to predict new instances. And I'm going to walk you through how this process works. So say we're trying to learn a model for the relation city located in country. That's this green edge here. As I said, the first step is to find a set of rules. And recall that these rules are structured such that they correspond exactly to chains in the graph. So what we're going to do is take each training instance, say Pittsburgh and US, and do random walks to see what paths can take us from Pittsburgh to the US without using that green edge. Maybe the first one we do is we go from Pittsburgh to Pennsylvania to the US. We record the path type that we took, which was just the sequence of edges, city and state, state and country. We keep track of what we found. Maybe the next time we go from Pittsburgh to Pennsylvania to Philadelphia to the US, we keep track of the path type that we took. We do this lots of times with lots of different path types. And after we're done with Pittsburgh, the US, maybe we have some list. We keep going through all of our training instances. And finally, we get a sum global count of path types that we saw that connected cities to countries that were instances of this relation, how many times we saw them. And then from this, we pick some number of these and use these as features in the feature matrix that we're going to compute. To compute this feature matrix, the value that we're going to use, so the rows here in this matrix correspond to entity pairs, for instance, Pittsburgh, USA, and the columns correspond to these features that we selected. The value is the probability of starting at the source node, in this instance, Pittsburgh, then doing a random walk that is constrained to follow this path type, and arriving at the target node, USA. What that means is, for this path type, we'll start in Pittsburgh, we'll go to the state that Pittsburgh is in, then to other cities in that state, then to the country that we know those cities to be in. If there's no noise in your knowledge base, this particular path type will get you from Pittsburgh to the US with probability 1, and that becomes our feature value. Then we go on to our next path type. This one takes us from Pittsburgh to companies that are in Pittsburgh, to other cities those companies are in, to countries that we know those cities to be in. This one also gets us to the US, but because of things like multinational corporations, this won't get us to the US 100% of the time, so our feature value is somewhat less than 1. We continue this process for all of our feature types, and this produces a row in our feature matrix. Just to drive this point home, this is what the feature matrix looks like. We have node pairs here, cities and countries, as rows. As columns, once again, we have these sequences of edge types, the path types that are our features. And recall that these correspond exactly to horn clauses, where the source, this node, it's a horn clause, as I showed you at the beginning. And the value here is the probability of starting at the source node, following this path type, and arriving at the target node. Then the path ranking algorithm says, take this feature matrix, run logistic regression, learn weights for each of these horn clause rules, and then use those weights to label instances that don't have labels already, so that you can predict new edge types, new instances of an edge in the graph. That's what PRA does. Okay, now I'm going to talk about some problems with this algorithm and how we can do better. And first I'm going to talk about the main problem here is the computational complexity of this. It's pretty bad. We have potentially, if there are n nodes in your graph or entities in your knowledge base, you have up to n squared rows in this feature matrix. For a particular relation, you might have a little less than that, but in the worst case, you have n squared. If there are relations in your knowledge base, and you're accepting sequences up to length L, you can have R to the L combinations. This is an exponential number of possible rows here. And even worse, for each cell in this matrix, you have to do a search. And a search takes time complexity proportional to the branching factor to the power of the number of steps that you take. here, if you have E edges in your graph, N nodes, this is the averaged out degree of at each node. So the time complexity is this for a search on this graph. Putting this all together, we get something that makes us not very happy. In practice, as I said, you can probably get rid of one of these N's. The initial search that we did tries to bound this a little bit by picking features that we think are useful. And you can do some dynamic programming to slash this exponent in half if you do some careful bookkeeping. But still, you're doing one search per node, so one search per cell in this graph. And so inherently, it's ugly. And it's even worse than that. The method that we use to compute this probability is rejection sampling. That is, we try to follow the path type. If at any point, say we've taken 2 steps and we get to a node that doesn't have this kind of edge, we go back to the beginning and try again. That's rejection sampling. If you're familiar with rejection sampling, you know that if you have complicated conditions at the end, the amount of computation you need to get a good approximate probability increases dramatically. Rejection sampling means that we can't have really complicated horn clauses here as features because computing the probability for them is very difficult.
But isn't that probably a good thing anyway? Because, shorter horn clauses are much more likely, exponentially more likely to be correct.
You can have some very short horn clauses that you still can't compute a probability for with rejection sampling if the condition is on the target and not on the source, because we're doing a walk from the source to try to get to the target. So yes, simple features are probably better, but this is still a problem because you're trying to compute this probability. Because of the way that we've defined the probability in this feature matrix, it makes things kind of ugly. So this, yes?
Isn't this matrix really a third-order tensor?
You could expand this so that you have node by path type, and you could see it that way.
And the random walks are kind of like PageRank. So I'm thinking if you did a PageRank algorithm on a third-order tensor, it might be a bit faster.
So the problem with a PageRank algorithm is that it doesn't use path types. I'm not aware of a PageRank algorithm that will use different slices of the tensor in some meaningful way. Maybe there is one, but I'm not aware of it.
So the modern search algorithm does look at different kind of links, like you see, they have features
Okay.
like this. But,
Okay. So in that sense, yes, it's similar, but I'm not really familiar with those
they
techniques.
forward sample. So they basically, the way they do PageRank is basically they don't take eigenvectors, right? They actually just forward sample.
Tamara Kolda has a paper on using a third-order tensor like this to implement the hits algorithm it's similar to this kind of thing.
Okay. We can talk about that later. I'm not familiar with it.
You've labeled this matrix as a city located in country, but is there anything that's specific to located in?
The only thing that's specific, on this particular feature matrix, we selected a set of path types using these instances as training data, because this is too big to keep the computation of this matrix feasible. We had to restrict some set of these path types, and that's defined by the training data here. This is a negative example. You can compute these probabilities for the negative examples. In practice, when we're actually doing this, we use a closed world assumption to forward this rejection sampling procedure. If we get to a country that isn't in our positive training data, we assume it's a negative. If you were given negative examples, you could do the same thing.
You're trying to predict missing edges. So how does that reconcile with assuming missing to be negative?
I guess one thing you could do is take all n squared possibilities, all cities and all countries, do a cross product, and you can compute a feature vector for all of them. And so in that sense, you could predict missing edges. Does that make sense? So we're just computing a feature matrix, right? And you can get negative examples however you want to get negative examples at training and at test time.
Right, but I think the question still stands because you can do that, and then you said, but you're using a heuristic approximation to that for efficiency.
You mean
where,
for the computing the probability, or for getting the negative examples?
um,
The heuristic approximation you said.
the heuristic approximation I was referring to is when you said you're using the closed world assumption.
For getting the
to
negative.
assume that
Yep.
To get the negatives.
Mhm.
So then when you do that, isn't that somewhat of an issue? Because you're training on a model where you say everything I don't know is negative, but the goal of the model, which is what Ashish was saying, is to predict that some of those negatives are actually positive.
That's a fair point. So at some level, you have to get negative test examples from somewhere. Let's just assume for a minute that they're given. And then the question is, how do I get negative examples at training time? I've done some experiments where I try to do something smarter. Probably the best answer to your question is just that, yes, because of the nature of the knowledge base, we're always going to have this closed world problem, and we're going to underestimate our precision. Like that's, unless you do a hand label of all of your predicted instances. I've done some experiments where I try a few different methods of getting negative examples at training time, and I found that this method that PRA uses of computing it isn't that different from doing, like you can take your positive instances, run a page rank to try to find other instances that are in some sense close to the positive examples that you have but are negative. But that's still using a closed world assumption. It's just trying to be a little smarter about it. So that's the tyranny of the knowledge base. We have a closed world assumption.
So is it fair to say that I'm conjecturing that when you're dealing with predicates where most of the instances are negative, right? Most cities are not located in some country, right? The number of countries is large and they're only located in one. Then that assumption at training time is a pretty good approximation of the truth. On the other hand, if you had a different predicate that was more promiscuous or whatever, more of the space, much more of the space, 90% of the things were true, then you'd get pretty different behavior.
I think that's more a function of what percent of the true facts are in your knowledge base than of what percentage of the cross product is true. Is that fair? It's how much do you know relative to how much is possible to know. And there are ways, I know of models by the Alan Ritter and some others that try to account for this. What I'm saying here is this is a feature matrix. I'm not specifying an algorithm for how to use the feature matrix. You could take this feature matrix and put it into Alan Ritter's model, for instance. So in the experiments that I've run, we use a closed world assumption because that's the simplest thing to test. You don't have to do that. You could do something more complicated.
In some sense, it feels like you could get away with just doing some heuristic on the length of the path, right?
You mean for getting negatives?
Yeah, because those things have to go somewhere, right? And so what you want to know is just that there's like a version to the baseline of distribution of where they go. What's the true, given these Pittsburgh USA true probabilities, how different is from baseline? That baseline is basically just based on the path, sort of, how distributed.
What's the fan out of this path? And that'll grow as the path length increases. So yeah, there's some to that. I guess all I would say is I've run a few experiments on trying to pick negative examples in a smarter way, and they were not statistically different from just the naive dumb thing. So I don't know, maybe you could do something smarter. Probably the better improvement here is to use something like Alan Ritter's model where you're explicitly trying to say, I don't know, versus I know this is true and I know this is false. Okay, so I was talking about why this is computationally hard. It boils down to the fact that we're computing these probabilities. So the conjecture is, why don't we just throw away the probabilities? It'll simplify a whole lot of things. If we make these binary features instead of probabilities, I don't have to do a search per cell. I can do a search per row. And I don't have to artificially limit the kind of horn clauses I can extract because I don't have the rejection sampling problem that I was talking about. I don't have to compute a probability. It's easy to say if a particular horn clause exists in the graph, it's hard to compute this probability. Okay, I'm going to so once we do this, it suggests a very simple algorithm for computing a feature matrix, and I'm going to describe what that is. So I call this subgraph feature extraction. As I said, this technique is very, very simple. So if you're given two nodes in a graph, the first thing you do is a simple search to characterize a subgraph that is in some sense centered around those two nodes. Second step is just run some feature extractors over this subgraph. This is really quite simple. To my knowledge, it's novel, at least in application to knowledge bases. So I'm going to describe an example of what I mean by this. So let's say,
I'm sorry to interrupt.
yes.
What I thought you were going to say was you compute some set of shortest paths. That would actually be simpler. It might not work as well, but couldn't you do that as well?
What do you mean some set of shortest paths between the
Well,
source and the target?
Yeah.
That's one instance of a feature extractor that I'm talking about. So we'll see that. Oh, you mean just the shortest path?
Well, you could compute, first of all, there could be a bunch of ties. So I'm saying you could compute the k shortest paths.
And those are instances of one of the feature types that I'm going to talk about. And we can do a lot more than that. So say that we're trying to predict whether Brad Pitt and Angelina Jolie are married. So the first step of this is to find a subgraph. So here are the nodes corresponding to Brad Pitt and Angelina Jolie. We do a little search, and we get this graph. Just as a little note, these /m's are intended to evoke how Freebase assigns entity IDs, as opposed to this in quotes that's a string that we saw in text. This alias relation is this noun phrase can refer to that entity. That's just what this graph means. So on the top we have some formal knowledge base like Freebase, and on the bottom we have extractions from text. Okay, so then given this graph, the second step just says extract some features. And what these features look like, well, the first thing is the obvious thing, given what I just talked about. We can extract PRA kinds of features, which are paths that go from the source to the target. So here, Brad Pitt to the United States to Angelina Jolie has the PRA path that we've just been talking about, citizenship, backwards across the citizenship edge. So the difference here is just this is a binary feature. That's an indicator instead of having some associated probability. And so it's very simple to extract. And there are 3 of these in this particular graph. But we don't have to stop with just PRA kinds of features. This next kind of feature I'll call one-sided features. They capture characteristics of the graph around either the source or the target. These would correspond to like the very short horn clause that has just a single rule. If you're trying to predict something about a pair, why is a one-sided feature useful? One way I think about this is that it's trying to characterize in some sense whether or not this node falls in the domain of this relation and whether or not this node falls in the range. For instance, you'd probably be disinclined to think that someone who was 10 years old was married.
What about doing a combination of the relationship between 2 one-sided features?
I'll get there. So just as an example, this feature would say that starting at the source node, you follow the path type that has the single edge, age, and end up at the node labeled 51. You could also recognize that this is a numerical value and be a little bit smarter than just using the actual node ID. Similarly, this feature says to start at the target node, follow an age relation, end up at the node labeled 40. And we can do this for citizenship. You could even do several steps if you really want. The usefulness of the feature will probably will go down significantly as the path length increases, but you could do this. And as Oren presciently brought up, you can compare these features, which is to say, if you notice that both the source and the target have the same path type going out of them, you can compare the nodes they end up at. So here, this feature says, from both the source and the target, follow the path type that's the single relation age, and at the source ends up at node 51, and the target ends up at node 40. And again, we can be smarter and say, these are numerical values, we can compare them. Similarly, another example, follow the citizenship edge from both. Source ends up at United States, target ends up at United States. This is very similar to a PRA path. It has a little bit more information because it's lexicalized. It knows what node it ended up at. And another example. Okay, this is another feature type. This one is due to Arvind Neelakantan at UMass Amherst. And the idea here is we can take a PRA path. This feature encodes the fact that there is a path from the source to the target that has this particular sequence of edge types. Instead of encoding the whole sequence, we could just take bigrams out of that and use those as features. So this feature then says there is a path from the source to the target that starts with the alias edge. Or there is a path from the source to the target that contains the bigram alias is married to. Arvind found these to be really helpful in a paper he recently published. Another feature type It turns out there are a lot of ways to say the same thing in text. And, and one problem with these kinds of feature models when you're dealing with text is that everything is symbolic. And so if the symbol is different here, the features don't match. And it's even worse because this is exponential in the number of path types. And so it just is really ugly if you have mismatching symbols. And so if you have some vector space embedding of the symbols in your graph, a simple feature you can extract is replace each edge type in a PRA path with something that you know is similar. So maybe you know that spouse of and Zweif is married, are similar to, is married to, you would extract these particular features in this instance. So the vector similarity features replace some edge in a path with some relation that we think is similar to it. You could go one step farther and just replace it with a star. So here we have these features say there is a path that goes from the source to the target that starts with some relation, then goes to is married to, then goes to alias inverse. Or this one, there is some path from source to the target that takes an alias edge, then some relation, then an alias inverse edge. Turns out this one is incredibly useful. And something like this is also very hard to compute with rejection sampling, for instance, because you could take any path there, and most of the time you'll not get to somewhere you can go across there. So these are the feature types that I've experimented with. You could probably think of a lot more. Just to drive it home, this is the feature matrix that we're now computing. The rows are the same, still node pairs that correspond to the domain and range of this relation that we care about, though now nothing here is specific to the particular relation. PRA would have a feature matrix that stops about here because these are all too complicated for it to compute. And now if we look at the time complexity of this, we're still have the same number of rows. But instead of doing a search per cell, we have to do one search per row. And that row is a two-sided search, so our exponent here is cut in half. And so the overall time complexity is something that we like a lot better. And so in addition to being faster, this is also more expressive. We have a lot more feature types that we can handle. And even in the PRA kinds of features, we can handle a whole lot more of them because we don't have to restrict ourselves to what we can afford to compute in computing this feature matrix, because there's not one search per cell.
Could you explain why did you say you have to do one search per row?
So remember, the process is given a row, which is a node pair, do a search to characterize a subgraph, and then run a feature extraction algorithm over it. So the one search is to get a subgraph, and then you just run some feature extractors over the subgraph that you extracted. Whereas with PRA, you do a first search over all of your training data to find path types to select the columns, and then for each cell, you do a search to compute a probability. With some caveats that you can make it a little bit less than one search per cell if you're smart, but it still fundamentally is essentially one search per cell, big O. Okay, that's the algorithm. What we're trying to do, once again, is to build a feature matrix over node pairs in a graph so that we can get information from a knowledge base and include it in machine learning models. And so I'm going to show some experiments in a few different applications that use this feature matrix to predict things. So the first task I'm going to talk about is knowledge-based completion. This is the same as link prediction in a graph. So the same thing that Ni introduced PRA to do. And this is given a knowledge base and possibly also some text, fill in missing facts in the knowledge base. Same thing, as I said, as link prediction. And for the experiments I'm going to show, the data that I used was the null knowledge base and subject, verb phrase, object extractions from ClueWeb, open information extraction triples from ClueWeb. And I'm going to evaluate this particular experiment on 10 null relations that I picked because null is noisy, and I picked these relations because they had reasonably high precision, that I could actually learn a model and test and have reasonable confidence that the experiment actually was valid. So first, let's look at how the different feature types worked, which ones are useful and which ones aren't. If you get PRA-style features, you do there's no baseline to compare against here, but this is what you do. Turns out the one-sided comparison, the one-sided features and the comparisons didn't help with these particular relations. I don't think I had any with people here, so this may be just because the relations that I picked didn't need these particular ones. But the other features that I talked about help quite a bit. In particular, the any relation feature is the most helpful. And an interesting note is that for all 10 of these relations, the highest weighted feature was this one, which says that these two nodes in these two entities in the knowledge base had some connection through text. Doesn't matter what that connection is, but there is some connection through text. Turns out if the relation you're learning is between cities and countries, and you see a city and a country in the same sentence, there's probably only one thing that that relation could be, and that's why this feature is so helpful. Recall, or don't forget that the PRA style features have the actual verb here, so we're not throwing away that information. It's just that this is very helpful to have in addition to the other stuff.
So there's something that I think is implicit in what you're saying. I just want to make sure I understand. If I understand correctly, the graph you're computing is actually based on the SVO or opening extractions, and then you're using the null to label those?
The
Or-
graph looks like this.
The thing that I'm confused about is, in the discussion thus far, you just said there's a graph that came from a knowledge base.
Has the knowledge base, and we're connecting it to SVO extractions with this alias edge. So this graph has both the knowledge base and the SVO extractions.
Sorry about that.
Okay. So now to compare to prior work. Here's PRA, Nielau's original algorithm. It does okay, I guess. Vector space PRA is a method I introduced a year ago that tries to be smarter about how we use vector space embeddings of the relations in the knowledge base as you're doing PRA. I don't really have time to explain how exactly it works, but it's better than PRA. But this subgraph feature extraction does a whole lot better on both mean average precision and mean reciprocal rank.
So how come PRA is worse than the feature ablation?
Yep.
Only your PRA features.
Because this has 240,000 features. PRA, because I have to do a single search per cell, I can only keep 1,000 features.
Performance issues.
Yes, it's computationally too expensive to compute this many probabilities for this many features.
And if you did like 10, if you did the same number of features with your binarized version, is it just terrible? Do you have all of it?
It's statistically indistinguishable. So I've done some experiments that take a PRA feature matrix with probabilities and binarizes it, and the performance is statistically indistinguishable. So the probabilities aren't actually helping anyway, turns out.
Start with that.
Fair enough.
Are you using the counts?
The paper that I wrote has that at the beginning.
Are you using the counts of repeated SVO triples? So for
No.
instance,
I'm not using it in this work.
because that could be quite a strong signal. And
Could
it's
be.
mentioned once in text versus 1,000 times. That would-
Yep. And good news is that's really easy to add in this kind of approach. And so what we can conclude from this little experiment is that SFE works. It beats PRA in both mean average precision and mean reciprocal rank. Recall, mean reciprocal rank is essentially how the precision of your top predictions. I'd say that's reasonably good as a precision for your top prediction. Mean average precision includes some sense of recall. It's like an average F1 or parameterless F1.
Can I just ask about your alias -1 link? I'm worried you've reinvented information retrieval here with this. I mean, could you?
What do you mean?
You're saying the strongest evidence you get in this
Is that there is some connection, right?
you can find the link in text.
So the nice thing, so I don't have the experiment here, but information retrieval, let's see, would correspond essentially to only taking those path types, right? And I'm combining that with information from the knowledge base, like, oh, hey, these two have a child that they share.
Right.
And
Did that help doing that combination?
I know that I've run experiments that only use the SVO as opposed to just this. And I don't remember the numbers off the top of my head, but I'm sure that the combination does better. It's been a while since I've run that particular experiment. Okay. And recall, this is significantly faster. It's an order of magnitude faster. So we're beating it in performance and in time by quite a bit. Okay, that's knowledge-based completion. I forgot to start my clock.
You're good.
Okay. So relation extraction, this next task. The main point I'm going to talk about here is that we can use these feature matrices in more than just logistic regression. We can incorporate this nice feature matrix that we've computed in some more complicated model. Relation extraction as a task is very similar to knowledge-based completion in that both are trying to predict new instances of a relation in some formal knowledge base. At least that's how I'm going to define this. The difference is that knowledge-based completion tries to predict which facts are true in general, and relation extraction tries to predict which fact is expressed by a particular relation, or a particular sentence. Okay? And because it's really expensive to label individual sentences, most modern techniques are what's called distantly supervised, where your only input is a big pile of text and a big pile of facts from a knowledge base. And you try to use some entity linking or correspondence to figure out which sentences contain entity pairs from the knowledge base, and use that as a weak kind of signal to train a model over the text to predict which sentences express which facts. One model for this, and because of the way this is trained, at least a lot of these models are actually jointly doing both knowledge-based completion and relation extraction. In particular, that's true of this one model, multi-R. This was due to Raphael Hoffman, who I think was here for a while. I don't think he's here anymore. It looks like this. This says for every entity pair and for every relation in the knowledge base, we have some variable representing whether that relation is true for that entity pair in the knowledge base. And then for every sentence that mentions each entity pair, we have a variable saying what relation is expressed by that sentence. These features here are dependency path features that you do a dependency parse of the sentence, you find the two entities, and you extract some features around the dependency path between them. This here is a deterministic OR that says if any sentence between this entity that contains this entity pair expresses a relation, that relation must be true in the knowledge base. The way this is trained is by saying some of these y's are observed, and then using that to to learn weights over the dependency path features that you got. Okay, that's multi-R. What are we going to do with this? Recall that PRA and SFE compute feature matrices over these entity pairs. And so we tried a few different ways of taking this feature matrix and putting it into the model. Turns out the one that worked best was to put a factor right here that has, so these are dependency path features, and these are features from the knowledge base about this particular entity pair. Notice there's nothing, this is for every sentence we're including this, which is maybe a little counterintuitive. But if you look at how this model gets its training information, it gets it from these y's, which treats all of these entity pairs equally in deciding which sentences to learn from. What putting this feature matrix here does, in addition to just giving the model more information to predict the y's, it biases the selection of which entity pairs to learn from toward those that have that are more canonically representative of this relation as seen in the knowledge base. Does that make sense? So this is a weak kind of supervision that treats all entities equally, and this factor lets the model decide which entity pairs it should learn these feature weights from more. That's one way of thinking about what this is doing. Now, the data that I'm going to test this on is a New York Times corpus made by Sebastian Riedel that's heuristically linked to Freebase, meaning they just did simple string matching over the Freebase names to find sentences with entity pairs. The graph that I'm going to use to compute the feature matrix that I talked about is the Freebase graph, minus all the training and testing edges from the sentences that we got. So just the PRA paths that I talked about previously. Baselines here are multi-R this Hoffman model that I described, and a related model called multi-instance, multi-label learning for relation extraction that weakens some of the assumptions made here in multi-R. You might say that those are unfair comparisons because we're using more information from the knowledge base. They're just using the knowledge base as distant supervision, and we're actually extracting features from it. This is a more fair comparison, you could say. This method is by Jason Weston and some others. They have this technique called trans-E that will generate embeddings for a knowledge base. So get a vector representation out for each entity and for each relation. And they use the knowledge base to get these embeddings, also similarly embed the sentences and use that to predict which facts are true. So this is a fair, both of these methods use the same information. You could say that about those, but we're using the knowledge base more. So how does it do? Turns out, to me at least, this improvement is pretty striking. So here's this black is the multi-R model. Here's the MIML-RE model. We beat those handily. We also beat this embedding model that uses the same information that we do by quite a bit. The particular reason for this, I think, is that, as Peter mentioned, you can view the knowledge base as a tensor. Tensors, especially knowledge-based tensors, have very high rank. This is trying to encode a very high rank tensor in a very low rank, whereas we can use the full rank with these symbolic features. And so we just trounce it in recall. And so what we conclude from this little experiment is that we can indeed use these feature matrices in more complicated models than just this logistic regression that it was originally introduced with. Okay, I think I'm running a little low on time, maybe. So I'll try to be quick with this question answering stuff. Actually, I'm just going to do part of question answering. Question answering is complicated. There are a lot of questions that need complex semantics. And I'm not going to try to handle compositional semantics here. I'm just going to handle, I'm going to try to build lexical models of verbal predicates so that we can, so if we have a simple question that can be answered by a simple lexical model that doesn't need composition, then we should be able to answer it successfully. That's the goal here. And I'm going to try this on two different data sets. The first is from here at AI2. I did this experiment as an intern almost a year ago. And then the second, and this is multiple choice science questions. The second data set is pretty different. It tries to do reading comprehension. This is out of Facebook AI research. I'm not totally sure how they pronounce that. I'm going to call it bAbl. Okay, so this first data set, you all, I believe, are familiar with this, so I don't need to say too much. The questions look like this. Which tool should a student use to compare the masses of two small rocks? With possible answers, a balance, a hand lens, a ruler, or a measuring cup. And to answer these questions, we have a collection of background texts that are fourth grade science texts, I think the science section of Wikipedia, some other related stuff. So I said we were going to build lexical models. What this means is I'm going to take each question and answer pair and convert it to some predicate with arguments. So here this is compare, balance, and the masses of two small rocks. And what I'm going to try to do, similarly, for this option, it would be compare hand lens, the masses of two small rocks. And what I'm going to try to do is build a model for each lexical predicate here that can score the arguments such that if I do this correctly, I can rank the correct answer above the bad arguments.
And you're getting the phrase, the masses of two small rocks, from a parse of the question?
Yes, yes. For this experiment, turns out I did this parse by hand. So use to compare, I simplified some things to do a little experiment. So to get data to build these models, we can similarly convert all of our background text into predicates with its arguments. This is just open information extraction. I'm just writing it a little bit differently. This was not done by hand. This was done automatically. These questions were done by hand. So to learn a model, we can take all of our instances from the background text for compare and try to learn something that can score these arguments. It's just, when you look at this model, it actually looks very similar to the knowledge base completion task, right? This is a relation between these. I'm trying to learn a model for this relation. The difference here is in the nature of the training data and the nature of the relation. This is an open domain predicate. I'm trying to learn a lexical model of language instead of some formal knowledge base relation. So the graph that I'm going to use to do this is the graph that's defined by these triples. Very similar to the other graphs that I had, except there's no formal knowledge base component. The model, as before, so for each verb, we're going to use logistic regression to learn a model to score the arguments, just as I did with knowledge base completion. And the features that we're going to extract from this graph will let us do inference to say whether or not a particular argument pair goes with a verb, even if we never saw that argument pair in the background texts. Sorry, I don't have an example. I guess I did have that quick example at the beginning. I'm just trying to be a little quick here. So how does it actually do? The Aristo system that you all know and love got 6. So I picked 24 questions because I thought these were answerable by lexical models and didn't need compositional semantics. That was the kind of question I was trying to answer. On those 24 questions, Aristo got 16 of them correctly. It probably does better now, but at that point anyway, it got 16. A simple baseline that just says, look up that triple in the knowledge base, which by knowledge base I mean the set of extractions, had pretty high precision but very low recall, as you would probably expect. And this system that tries to build a model over these model for each lexical predicate does comparable to Aristo on these questions. So from this experiment, I think we can conclude that we can indeed successfully build useful lexical models that perform inference over a set of extracted knowledge. And very quickly, this other data set is reading comprehension. So the questions look like this. There's some passage, and then a question with an answer. And the goal is to, I guess, here the lexical meaning of is depends on the context. So you can't just build a model that only uses background information. You have to incorporate the discourse context into this somehow. So just to give a really quick example. So here, okay, so to get training data from this, I find a set of candidate answers here by just looking at all the nouns in this discourse, and then the one that corresponds to the actual given answer is positive. Those are negative examples. So anyway, from here, what I'm trying to do is to build a lexical model for is in that can score whether the apple and the office are a correct argument pair given lexical information about is in and the discourse. So what we need here is to know that you are somewhere that you have went to or that you were or that you moved to, and that you are only in the last place that you were in. So lexical information from the first part and discourse information because you need to know stuff about this sequence of text.
So I think you already partly mentioned, but I'm not sure how you would do that temporal aspect. So if you have a relation for when John went to office, John went to kitchen,
Mm-hmm.
and you somehow capture the temporal nature of the discourse.
I will show you. So, so the technique I'm going to use is the same, right? I'm talking about how to do feature extraction over graphs. So the question here is how do we represent a graph that can encode all this information in a way that we can build a useful model from it. So to build a graph, we have all of these sentences. Each word in each sentence is going to be a node in this graph. We can include dependency parse edges pretty easily. And then to get discourse information in here, we take every noun phrase and link it to the previous instance of that noun phrase in the discourse. The black edges here contain lexical information. Went to the kitchen. So capturing this captures lexical information about what corresponds to is in, and the red edges are discourse information. And the paths that go through this graph from, say, Apple to John to previous John to office back here will encode both discourse information, these red edges, and lexical information, the gray edges, black edges. Sorry, I'm brushing this just a little bit. What I'm going to do here again is just build a lexical model for each verb phrase in the question sentences, like is in. And the features, as I just said, are going to incorporate both discourse information and lexical information by virtue of how the graph is encoded. And how does it do? On questions that are simple, that can be answered by a simple lexical model, we do pretty well. This MNN here is memory networks. It was a method developed by the same people who produced this data set, intending to do actual question answering. So the model is much more complicated than the simple lexical models that I'm doing. And on these question types, I would say we're doing pretty well. We match the performance of this method on most of them. I didn't try this one because you can't count with a lexical model. You need,
Standard breakdown.
say that again?
This is a standard taxonomy that they provide.
Sorry, I should have said that. There are 20 question types in this data set. This is the first 10.
Is this the Facebook?
Facebook AI research, yep.
So for what it's worth, the IR models on this beat the memory networks as well.
Okay, I didn't know that. Okay, that's good to know.
Did you automatically build the graphs, or did
Yes.
you?
So the thing I did by hand here, it is straightforward, but just because this was some preliminary experimentation, I took this question answer pair and by hand converted it to a declarative sentence for each question type. You could do this just with a simple parse of this, reverse the WH movement and replace the WH phrase with the answer. I did it by hand instead of writing code to do that because this was a quick experiment. But I don't think that's a huge barrier to this method in general. Okay, so on the simple question types, we can do reasonably well. On harder question types, these take more information than I gave the model, and so I don't really expect to beat the actual question answering system here. But we can still do reasonably well on these question types, with an average accuracy of about 83%. What I conclude from this little experiment is that we can indeed build lexical models that incorporate both lexical information and discourse information. If you combine this with the previous question answering experiment, I think it's reasonable to say we could build models that can incorporate discourse and background knowledge in a reasonable way. I don't have a data set to test that on. If any of you know of a good data set that would test that, I would be happy to know about it. So to conclude, I'm going to briefly say where I think this research is going. I just talked about building lexical models for question answering. What I would really like to do is incorporate these lexical models into some sentential model of compositional semantics. Jayant Krishnamurthy, who's not here today, has a nice model. Oh yeah, he has a nice model that he's presenting at ACL right now. That models, it does a semantic parse over open domain text using a matrix factorization model as its underlying lexical semantics. I think it would be pretty straightforward to replace his matrix factorization model with these graph-based models as the model of lexical semantics that underlies this semantic open domain semantic parser. And I think it's pretty clear that these graph-based models can perform better than matrix factorization models. Jayant's stuff can't do anything with discourse. It can't do very complicated reasoning over background knowledge. I think it'd be pretty simple to replace the matrix factorization with this. And one simple of it, the relation extraction experiment where the PRA features did way better than the trans-Z embeddings, I think is good evidence that this graph-based stuff is better than the factorization techniques, at least in some instances.
Don't you need graph to be turned into a matrix or a tensor?
Sorry, the factorization, low rank embedding, that's particularly what I'm talking about. Because the tensor is high rank, particularly with these kinds of knowledge bases. If you have a slice of your tensor that's a permutation matrix, or essentially a permutation matrix, you just can't find a low rank embedding for it, and so you lose a lot of information when you get a low rank embedding. And that's why I think these methods do so much better in some instances, not in all instances. Another direction I'm heading, I've been starting work with Abhinav Gupta, who I think has been talking with people here at AI2, on using this graph-based reasoning to improve image understanding. So if you have a pile of images, say about cars, and you have a pile of facts about cars, that cars have windshields and headlights, can you use this to do better image understanding? I think these kinds of approaches are potentially helpful for this kind of task. Okay, so to conclude, I think that I've shown sufficiently that feature extraction from graphs is a powerful way to incorporate knowledge-based information into machine learning models, particularly models of language. Thanks.